what's my segment selector? Remember, we stole the top 2 bits. Here's my segment selector. So it turns out we're in code, aren't we? Aha, so now I use the code segments based on bounds register. So, for the code segment is at 32K. And unfortunately, when we do this on an exam, you're going to actually have to do math. 1K is 1024, right? 2, 8, 12, 3, which is 8, 6, 7, 2.
Looks like easy math, but can you bring your calculators?
I can't hear you.
Can we bring our calculators just for that?
You can bring the ones here.
Thank you.
I even have several computers here. I'm not going to use a calculator. Okay. Doesn't mean I'm going to get it right, so I want you to check me as I go along. Okay. So now, here's our offset. And it turns out our offset's just 100, isn't it? Right? So for this particular process, virtual address 100, based on the information we have, is located in physical memory at address 32868. Now, how many of you noticed that 32868 is bigger than 4K? Okay. What I want you to know is that for the physical addresses, we get to use all 14 bits for the physical address. Physical addresses don't have segments. They treat all of memory as one huge array. So the segments are smaller, so they can be moved around. So we have more of them in memory. So we're going to use all 14 bits, excuse me, for the maximum amount of physical memory we can have. Right? Which says that we can have, 16K in this memory system. So does that make sense? Can I erase the, I want to go to the next number, 4200. So this next one.
Out of curiosity, why is it a 14-bit example?
Because that's the number we chose.
Yes.
Because if I make it 32-bit, we're going to be here forever doing that.
Yeah, but I guess I was just curious because I know there were 14-bit systems, and is that because
There was?
weren't there? I thought there were.
I thought there were 16-bit systems.
Oh.
There could have been 14-bit systems.
I was just curious because that sort of comes out neatly with the fact that the selector is the first 2, and that the rest are a power of 2. Right? If you have a 14-bit system, then you have 2 bits for the selector and 12.
If you have a 31-bit system,
Yeah.
you have 2 bits for the selector, then the rest is a power of 2 as well, right?
Yeah, I guess you're right.
That's the problem with binary.
Yeah.
Everything's a power of 2. Everything fits in a power of 2 when we look at the
Yeah.
maximum size.
Okay.
So what we're going to have you do now. Yes?
So in this example, we have 2 bits for the selector and 12 bits for the memory address.
Correct.
Would it be 14 bits for the memory address and a 16-bit system?
No, we have a 14-bit address space, and we're going to steal 2 of those for the selector. So that gives us 12 for the offset. Okay, well, did I say 14 for the offset? Hope not. Huh?
I just got confused.
Yes, well, I've also said 16 a couple of times here too, and I apologize for that. So now what I'd like to do is calculate 4,200 in base 10. And what I'm going to do is give you guys a few minutes to calculate this. And then we'll go off and take a look at what's going on. How many of you went into computer science because you knew you'd never have to do math ever again? How many of you have been consistently disappointed in every class you've taken? CS201, I go, you know, n plus 1 is not strictly greater than n in computer science. And everybody goes, what? N minus 1 is not strictly less than n in computer science. At that point, everybody goes, you know, business is starting to look like a really good major. Because you can never have so much money that it flips over and becomes negative money. But inside the computer, you can do that, potentially. That'd be a bug, but. Sir?
I just wanted to ask you, why did you subtract 64?
Because the largest power of 2 below 6, below 1 hertz.
Oh, that's what you did.
Yeah, just converting decimal to binary. So what's our first thing that we're going to do? Besides put it into the Microsoft calculator set on programmer mode. What's the first thing we want to do?
Convert to binary.
I want to convert it to binary. So who's got to convert it to binary? Okay, so only one? How many are still working on converting it to binary? Okay. So Henderson, from right to left, tell me what your numbers are.
It is from right to left. 0, 1, 1, 0. 0, 1, 1, 0. 4 zeros. 1, 0.
Okay. Yeah, that looks good to me. All right. So the segment selector is equal to what?
That's not right, that should be 1000 for the rightmost 4 bits.
1000?
Yeah.
Oh, well, I'm wrong. That's nice.
How could you?
I know. I'm shocked.
See, it's not my fault now. See how I got sneakily did that? What's our segment selector?
Got it.
0, 1. Which is interesting now because this is my offset, isn't it? So what's my offset?
So you're in big data.
Okay. What is my offset in decimal? 0, 1, 2, 3, so that's 8 plus 1632 plus 64, right? 6 plus 8, 104 basically. Okay. Where is this located in my process space? In my process space, my virtual. So which segment am I in?
Data.
We're being in data. So most likely this thing came back from Malik. Right? Could be an address that came back from Malik. So now for data we have 34K, don't we? Okay. people got 34,920? Huh? Yes.
So why are you multiplying by 2 to the 10? That's 1, 0, 2 to 4. Aren't there 11 bits outside of the segment?
Yes, but we count from 0. Okay, so the number of n, the maximum number we can have in n bits, because we start at 0, is 2 to the n plus 1. Now 2 to the n plus 1 minus 1, the actual value is 2 to the n minus 1, right? 2 to the n then minus 1, number of bits, but we start counting from 0. So the number of values is going to be 2 to the n plus 1. Okay? So if we have 11 bits, the maximum value is 2 to the 12 minus 1, but the number of entries is 2 to the 12. And by the way, that's the reason why they picked a 14-bit address space is because 4K is used a lot in computer science. So it turns out to be a number that, once you've been wandering around systems for a while, it's a number you don't forget. And that's why I try to tell everybody 1K is 2 to the 10th, and it seems to help. So did anybody else get this number? Okay. Anyone else hoping to get this number? Did I make any mistakes? So now, it turns out, it's like, that's all well and good, Mark. But what happens when gross negative is set to 1? Turns out that is the tricky problem. So what I want to do is point out how the stack segment is organized. Okay. So here's the base for the stack segment, which in the Intel world is called the segment selector. Excuse me. The segment selector and the code segment is going to be CS, and the data segment is going to be DS. So this is stack segment selector. And note that it grows down. But offset is unsigned. Which means the offset is a positive number. But base plus offset will automatically put us outside this segment, won't it? There's got to be something else. All right, so let's say that at any particular point in time, this is how much room our stack is using. But it's not using its entire segment. It could grow up to that much. And it turns out that the size of the segment, the biggest you could ever be, is the maximum segment size. So now, this is where we take into account that the offset is from the lowest possible address in our segment. What is the lowest possible address given the information on the board that we could have in this segment? Base, yeah, it's going to be base minus maximum segment size, isn't it? And this is what the book says to do. Just memorize this. Okay? Instead, I say, let's do minus 1 times gross negative times MSS all the time, and then add base plus offset. Okay? If it grows positive, this falls away. But if it grows negative, this gives us this, doesn't it? Okay. this is the reason why I use this formula, is because how many of you have better things to do with your time than memorizing a bunch of arbitrary formulas? Nobody does? Okay. Well, it turns out I do. And I was like, I'm not going to memorize 2. I'm just flat out not going to do it. Instead, I'm just going to memorize 1. All right? Then it just means that I need to know to annotate any diagrams with gross negative. Because I've looked, and this formula doesn't show up in any of the textbooks I've looked at, and I've got like 10 different textbooks. They all use 2 different formulas. I have no idea why. So base minus maximum segment size now puts us here. And our offset is relative. Notice it's not relative to the space I have in use. The top of the stack is at the stack pointer. But the stack pointer moves, doesn't it? It's a variable. That's no good for us. We need to calculate our offset relative to a fixed number. A lot of these numbers are assigned at compile time. Okay. Now, let's say that what we're currently using is 2K of our 4K. And I want to know what the address is halfway into the stack. What's that address right there? Now, we know how far it is into the stack, don't we? How far is it into the stack? Who's got an answer? How many people say 3K? 1K? Some other number? Okay, it turns out that if the stack is 2K and we want to get halfway into it, we want to go 1K into the stack, right? That's not our offset. Okay. This is where it gets ugly. This is our offset. How far away we are from the lowermost address that we could generate for this segment. So, and I'm going to phrase this in a way that's even more confusing than I normally make it, okay? But there's a reason for it. I want you to be confused in this. In this example, in order to get 1K into the stack, the offset must be 3K. All right. Notice I didn't say the offset into the stack. Well, we could say offset into the stack or address into the stack as 1K. But the offset, that is the value in the virtual address, all right, is going to be 3K. Because it's the offset against the lowest address we could have in this segment. If we're only using 2K, that lowest address in our segment is outside of our current use of the segment, isn't it? But it's a fixed number. We're not going to access it, we just need to use it for a calculation. Okay. So, let's go work an example. So, we saw before was that our stack was sitting at 28K. So we know we go from 28K down to 24K, right? And we say it's currently in use as 2K, so we know it goes from 28K down to 26K. If we want to get halfway into there, we know that we want to get to 27K. All right? And that's physical memory. So now we have to figure out how we're going to do this. So, we could just say, hey, we're trying to get to 27K. Let's just turn that into into bits. Okay? It turns out that while that's fine to do that, usually our stack's not so convenient as to just give us multiples of 1K. All right? So it might be, we're 1,473 bytes into the stack. What's our offset? That gets kind of ugly. All right? But, back over here, it turns out that we're going to try to get 1/2 into stack, which is currently 2K. All right? And we had maximum segment size of 4K. It turns out if we want to get to that 1/2 way into the stack, we were able to go back out and say, well, in physical memory, it's going to be 27K. Right? Yay! But it turns out that's not the number we need. What's the actual offset?
$3K?
3K. Why? Why is it 3K? Does anybody hazard a guess? Turns out the lowest address is going to be the base, 28K, minus the maximum segment size. And the MSS is